realize I should have gotten on a different button. I don't know if I can screen share from here or not. But I'm gonna share some work that Mike and I have been doing. How is everyone this morning?
Doing well, thank you. Are you getting settled back in after your trip to China?
Yeah. I'm working overtime, so to speak, on trying to get a prospectus together for IMC. So it's going well, but it's I've been working all weekend to get this done. So yeah. Let me see if I can.
Yeah, I noticed your mic is. I have you up all the way on my volume, and it's still a little. You're not coming across real clear. It's maybe a little muffled.
Hang on a second. Is that better?
We'll see as you talk.
Okay.
Yeah, I mean we can. I can hear you. It sounds like you're in a. It's just not real. Maybe a little muffled or.
Yeah. Sorry. Is the only headphones I've got.
Yeah, it's probably the device that you're using, and you probably don't have much control over that. But yeah, with my volume up, we should be able to get through.
Okay. Sorry. Zoom is acting up on my. Okay, so I'm switching devices, so 1 second.
Okay.
Okay, can you guys hear me?
Oh yeah, much better.
Okay. Well, I switched devices so I could do a screen share.
Okay.
But I'm glad I had the effect of improving the audio as well. Okay, so do that and that, and now bring this. Do a screen share and okay. Can you see this?
Yes.
Okay. All right. So what I'm going to do is walk through. So this is the ladle construction for the proof theory for a minimal interactive rewrite theory. So, uh, and a rewrite theory is interactive if its rule has, if it has a rewrite rule that is bipartite, in the sense that the left-hand side of the rule is made of a term constructor that takes at least two terms. So a couple of examples are lambda calculus, where you have an application of an abstraction to an argument, which is, and then beta reduction substitutes the argument for the variable in the abstraction. Or the cum rule, as in the pi calculus, where you have a parallel composition of an input guarded process and an output. And the cum rule then, at least in the case of the row calculus, substitutes the code of the output for the variable in the for comprehension. So those are a couple of examples, and there are dozens of others. But the point is to illustrate that a system is interactive if the rewrite rule, the left-hand side of the rewrite rule, takes a composition of two terms and then reduces it down to a new term. So that means we have one term constructor, K, which takes two terms and produces a term. So in the case of lambda calculus, that would be application. In the case of the row calculus, that would be the parallel composition. And then, just to get things off the ground, we're going to assume one constant, C, along with, since K might not be commutative, we're going to assume that there are left and right identities. Now, you might have the existence of one, not the other, as in the lambda calculus. So in the lambda calculus, you have a right identity, but you don't, or sorry, you have a left identity, but you don't have a right identity. In the case of the row calculus, you have both, but they are the same because the operator is commutative. So zero is or the stopped process is the identity for the parallel composition operator. So K is our compositor for reduction, our term constructor for reduction. C is our constant, and then you have left and right identities. And notice that since we have distinguished C from the identities, that means it's not the trivial thing, right? It's some generator. And then we have a rewrite rule, a single rewrite rule. We're just talking about the minimal case here. And then we use the source and target maps to say how the rewrite rule operates, right? So when the source is a K of TU, then the target will be some function of T and U. So that's our input, right? So to ladle, we are given an input like this. And the first step in ladle is to add a resource context. So we're gonna transform this theory into this theory. So we're the left and right remain. So that's just I'll add that. It's just understood that they remain, but I'll keep them there. And then the only thing we're doing is we're adding this context, resource context R. Now you can either think of it as a evaluation context, taking a T and returning a T, or you can think of it as a constant. and that you put the constant into K in order to get an evaluation context. So either of those are it's equivalent to the other. For this presentation, I've used it as an evaluation context. And so you modify the rewrite rule so that you only get to rewrite if you have an R wrapped around your term constructor. Otherwise, the term constructor is frozen. So I can get rid of this right now. That's no longer needed. And that's it. That's the only thing that adding the resource theory does. Then we add a notion of context, a single hold context. So to this resource theory, we're going to add another constant, which is a whole. And we're going to add a sort, which is what we'll call chi of t. So this is separate from t, but it's related to t, which is why we call it chi of t. If t is the sort of terms, chi of t is the sort of contexts. And so whole is a constant, right? It takes nothing and produces a chi of t, which is just whole itself. And then we have k left and k right. So this is k sub whole, distinguished from this thing, which given a context and a term produces a context, right? So if you had a whole and a term, then it would be k with the whole in the left and the term in the right to produce that context. And then k whole right, which would be, again, just putting the whole in the right-hand side. Or if you've got a context, some richer, deeper context, you're putting that context. But what this does is it keeps the, you're always going to have just one whole. You can't have multiple wholes in the term in this presentation. So it's linear in a certain sense. And then there are left and right abstraction operators. So given a context, we're going to lift it to a special kind of context, which we know we're allowed to treat as something where we can fill the hole. And then there's a substitution operator, at sign. So given a context and a term, we produce a term by putting the term in the hole. And then again, we have what we had before. We have the resource, the evaluation context, the rewrite rule, and there's a substitution map constraint, which says that when you apply at of t to whole, you get t, and you can distribute the map in. So if you have a k whole left with the context a t and a u here, then you just move it inward. So basically, you just keep pushing the term deeper into the context until you hit the hole, and then that's how you put the thing into the hole. So that's all of this stuff is preliminary. It's just necessary. But what we're doing is we're presenting a Levere theory version of what's well known in programming language semantics. So we've made so the fresh thing here is that we've supplied a Levere theory presentation of contexts. And that's important because now we can make this to monads. So essentially, there's since we've got this as a Levere theory, there's a corresponding monad lying around. So each transformation we start with a Levere theory, a graph-enriched Levere theory, and we move to another graph-enriched Levier theory. And then we move to another graph-enriched Levier theory in a step-by-step fashion, right? So at each step behind this Levier theory is a monad, which is kind of important because Ladle is the logic as a distributive law. The distributive law operates on monads. And now we have a notion of left and right arrows. So basically what this is, you can think of this as a kind of generalized implication, but this implication is powerful in the sense that it allows us to unify modal logics and ordinary functional types, like in the simply typed lambda calculus. So we can get a single account of the Hennessy-Milner modal operators, as well as the simply typed, the arrow type and the simply typed lambda calculus. So it's straightforward. This thing is going to be the set of terms from our theory, such that for all u that are of type A, so you're given two types, A and B, and for all the u in A, the existence of a rewrite of this form implies that V is of type B. So notice that the context is on the right-hand side, so that's the arrow moving in this direction. When the context is on the left-hand side, the arrow moves in that direction. And notice that we flip around the A's and the B's. So that's our notion of arrow. Basically, it's a generalized form of residuation where you're plunking the rewrite rule in the middle of the residuation. So that's the key trick in a lot of this. And now that gives us our types. This sort of fun, a type tau is either our ground, which is top, right? So which is all the terms you could generate, or it's the arrows. So tau arrow tau, or the tau right arrow tau, or tau left arrow tau. The constants all get lifted as types. We recognize that types are set-like gadgets. So there's the empty set and then unions. And then we recognize that if you have a type, you could lift it with a resource. If you have a pair of types, then you could make a K of those two types. And then these are the interesting bits. Essentially, you have two different kinds of operators related to the rewrite rule. One is suspending the computation. So you have a K, and K without a resource suspends the computation, right? So if we deny a K a resource, then it's got all it needs to run a computation except the resource, right? So you can think of it as like a thunk, or it's just a suspended computation. So it's like wrapping things up in the at operator in row calculus. So you're pausing for a bit, and then when you unpause by supplying an R, you need to you need to say whether or not you're going to continue in parallel or in serial. So when you so this one gives the ability to unpackage stuff that's in here, and this one gives the ability to unpackage stuff that's in here. So we freeze the computation, but we can't get the data out. This allows you to extract the data. We freeze the computation, but you can't get the data out. But this allows you to get the data back out. And then when you cut these two together, so cut in the sense of the cut rule in logic, you can either run the computation, because you're going to have computation elements here and here. So you can either put this one with this one, or you can, and this one with this one, or you can put this one with this one and this one with this one. So that's what I mean by parallel versus serial. And that's it. That's all the types we have. So it's fairly straightforward. And then we have some abbreviations. It turns out that there are lots of different negations that we can form. And they are related to basically the arrow type. And what's called the double negation, or call CC interpretation of negation, which, by the way, is at the heart of R space as well. But essentially, you have a linear style negation by going to the right identity, and you have the dual of that, which is going the left pointing arrow going to the left identity. But you also have a more classical style, or classical is not quite the right word, but you have a negation that's like Boolean logic by using the arrow to the empty, the right and you also have a one on the left by using the other arrow. And you can get other negations as well if you're clever with these types. But these are common notions. And then I'll just go through a couple of these rules rather than go through all of them, because I've already been yammering on for quite some time. So every constant term has a corresponding type. And so you can also apply this to the left and right identities because they're effectively constants. And then tensor is, I've got gamma thinks that, or with this typing context gamma, I can derive that T is of type tau, and with this typing context delta, I can derive that U is of type tau prime. Then gamma together with delta on the left-hand side, so I need both of these contexts. Think that K of TU is of type rho tensor tau prime. So this is what I'm saying. This represents making a left-hand side of a rule, a K, but without the resource. So this is the tensor operator. It's like pairing, but it's not pairing. And then we have the corresponding dual to that, which is par, which is if I have a single gamma that thinks that T is of type tau and U is of type tau prime, then I get that par TU is of type rho par tau prime. So effectively, we're packaging up these two terms in a special term that we've added for this stuff, and I should add those to the contextualized theory, but it's very straightforward to do that. And now the interesting bit is if I have a par and I have a K, I can cut the two together. And when I cut the two together, the par one takes the T prime with the T, and the U prime with the T prime perp with a T perp with a T and a T prime perp with the T prime, and produces a term like this, right? So I cut the K with the T. I have a T prime cut with a T and a U prime cut with a U, and then I cut those two together. So these reductions happen in parallel before we reduce their results. And what this will result in is R with the right identity. So this is basically hiding all of the work that happens in here. We can't see it, which is what's why this is sort of like a category, because we know that this is a T perp, and when we cut a T perp with a tau perp with a tau perp with a tau, that should result in an RK. And this is a tau prime perp cut with the tau prime, that should result in an RK, and then a K with an RK and an RK should just be a K, and then the capital R just carries along. So this is exactly what we want out of a cut rule, right? It mimics what we expect from a category, right? Because when you wire if I have an arrow from A to B and an arrow from B to C, when I wire the two together, the B's disappear, and I should only get an A to C. So this is effectively mimicking that idea, but I'm not presenting the category. I'm just presenting the proof theory. So we have a similar idea for the serial stuff. So when you cut it, right, the T goes with the U, and the tau T prime goes the U prime, right, and so they run in that order, but we still get the same type out at the end. So that's the idea of parallel versus serial. And then notice that the usual cut rule, where you have a tau perp and a tau, is just a special case of either one of these, either one of those arrows. So you can derive this rule from the other two rules. And now the other thing is the context. So if I have whole is of type chi t, thinks that whole is a type. That's our axiom, right? So we get off the ground for context. So in the same way we get off the ground for terms with the constant rules, we get off the ground for context with the axiom rule, right? So it basically says if I have a whole that takes a context, or that is a context, then I have a whole that is a context, right? That's the basic idea. And now if I have a gamma together with the whole, thinks that U is of type tau, then I can form a U bang. So discharging the hole on the left-hand side of the turnstile, because I recognize that there's a hole somewhere in U, and then I turn this into an abstraction. So it's an arrow type now, meaning I can apply it. And then we can do the same thing on the other side. So if I have a hole, if gamma together with a whole think that T is of type tau, then I can get a bang T as opposed to a U bang, right? So bang T is an arrow type pointing the other way. And now we can do cuts in the same way. Now, and what's going to happen is the taus will fill the holes, right? And we'll get the corresponding and we add the resource, and then we get what's left over from this. So again, this is exactly the categorical thing. Now we have honest to God arrows in the category, and this is what's left over. So we get the tau prime in the tensor. And the same thing happens for the cut right. So you're filling the hole with the U. Sorry, you're not filling the hole. You're putting them together inside a K, which will do what needs to be done, essentially. And the same thing is going to be true for the other gadgets. So this one was for pars, but you'll also get this one is for the parallel version. This one is for the serial version, and let's see, and I think that's, and then we have, let's see, yeah, that's that. Yeah, that's it. That's all that's left. So you have parallel and serial, and then notice that we have in this formulation we have turnstiles which have things to the left and the right of the turnstile. So they're what's called double-sided turnstiles. So essentially, in this situation, there's only one thing on the right, and there can be multiple things on the left. So that is essentially an intuitionistic flavor of the logic. But you can also give a classical flavor of the logic or the type system. So let me just, yes, there it is. So now, so in the intuitionistic setting, this is your notion of axiom. You can, if you're dealing with what are called double perp closed terms, if there's, then your axiom can be, you can flip this to the other side, and when you do so, you say that this whole needs a t rather than oh, these should be tals, but this whole needs a t or tau rather than since it's over here, it needs it. When you move it over, you need to say that it's a perp, meaning that it needs a tau. And this is one that supplies it. So you're treating the two copies of the whole as if they are a wire, right? You put a T in, you get a T out, right? So these are two ends of a wire. And now the interpretation of comma on the right-hand side of the turnstile is tensor, which is just the K constructor, right? So when we do something like this, we're really saying that. So for example, if you expand this out in the case of application, this is tau to the left identity, and that's just our usual whole. And so if you run the meaning of this, you get exactly app of ik, right? So t is supplied, t is provided, and you can't see what goes on in the middle. So then, oh shoot, I have to go and fix all these t's to tals. It's a typo. I need to go back and fix. But essentially, this is a recapitulation of those rules, but only with the one-sided turnstile. And you get these two different flavors. These two different flavors are distinct if you have instances of double perp in interpretation that don't coincide with the double perp closed terms. So that's why we have both of these presentations. You have both a classical and an intuitionistic hinging on whether or not that exists in your rewrite system. And that's it. That's the whole system. So what we've done is we've identified the minimal theory. So here's your minimal theory. Now, of course, it can be much bigger than this. You can have lots of Ks. You can have lots of generators. You can have lots of rewrite rules. But in the case of just the minimal one, where we have a single K and a single rewrite rule, these are the steps to get, from the input monad to the monad or Levere theory, over which we can now generate a type system and the corresponding term assignments, which are also proof rules. So the way to think about this, and the reason I have them color-coded, is red things are term, and if you just look at these rules in terms of red things, Then these are term formation rules that are going to make sure that you you form terms that always result in some particular property. Where in this case the property is going to be the left or the right identity, but it could be other things as well, depending on how you set this up. And so in other words, so Gilad Brock has this idea of pluggable type systems. So we can support that notion by changing the property that the type system guarantees. And then the blue side are formulae or types. And so now, if you just look at these in terms of the blue things, these rules are proof rules. They say how to get from valid formula to valid formula. And then when you put them together, they are term assignment rules. They say how to get well-typed terms. And as long as the term is well-typed, then it exhibits the property that you're interested in. So that's it. That's our type system, and notice that it hinges on this idea of a resource. So we're essentially, what we've done is we've given ladle as an abstract characterization of cost accounting. Now, another interesting point is that this crucially depends upon two ways of suspending terms, right? So, and they're effectively isolated or independent. So, a term is a term is going to be suspended either by denying it the R, or it is suspended by an abstraction, right? Using a context. So if a K has a hole in it somewhere, then it can't go forward, and we can see that because the rewrite rules don't work on context; they only work on terms. The other interesting piece is that we have our original theory. Sorry, the resource and contextualized theory is. Oh, sorry, I got distracted by a typo. Maybe I'll just leave it there. That's a lot to digest. So let me just stop and see if there's some questions or comments about what I said.
This sort of took me back to Murray Turov teaching us how to write systems in the 70s, and his statement that all systems have an economic basis. And it seems like you've proven that here.
Yeah, that's essentially what I'm saying. That's essentially what I'm saying. Although R is not really economic, it can be economic. So the comment I was going to make is that we kind of snuck R in. Like R could be something, some really rich theory, right? So for example, you've got some VM and it's running on some hardware, and R is the hardware. Well, hardware is its own theory of computation. So inside this and hardware is the evaluation context, right? So through the evaluation context, we snuck in this whole alternate theory of computation. That's it's not necessarily, it is economic, but it's kind of generalized economics. But what you could do if you want to keep everything closed, is you could take R as a different version of our original theory. So you can do this mutual recursion thing, right? So you could say that you have two colors of this theory. Since I've used red and blue for terms and types, I'll use, I don't know, purple and orange. So I have a purple version of the original theory, and I have an orange version of the original theory. And then when I introduce the R thing, the purple theory is R for the orange theory, and the orange theory is R for the purple theory. So now I've done, now I've remained entirely inside the original theory. But I provided a notion of an evaluation context, right? So they're, it's just like my red-black sets or variants thereof, variants of that idea. So the R is the theory the resource theory becomes self-contained, but now the R can be as rich as you want it to be. In terms of its computational mechanics. So it's a long-winded answer. So essentially what you're saying is correct, but I just wanted to point out that in this setting, it's highly generalized.
In a sense, it could, I mean, in an ecology of expressions, would it be a catalyst?
Yes, R is like a catalyst. R is exactly a catalyst. But now you want to ask yourself, well, catalysts have internal structure and they do all this magical stuff.
Right.
Yeah. So.
So R can be some cryptographic algorithm, maybe. Or...
R could be a cryptographic algorithm, for example, right?
Greg, I have a more base. Go ahead, Tomislav.
Oh, just one question about a serialized and parallel way of
sure.
Parallel constructors. If we model something like lambda calculus, do we need parallel constructors?
Yes, it doesn't mean serial or parallel in execution. It means how I mean it in terms of like how we're wiring circuits. So for example, we have an SKI implementation down here. So we run it for SKI. In the case of, so when you form, so notice that you're going to have a par, sigma is the rewrite rule for, S, right? So you have a par X, Y, Z, and you have an S, X prime, Y prime, and Z prime. Okay. Now in parallel, the X goes with the X prime, the Y goes with the Y prime, and the Z goes with the Z prime. In serial, it goes, we've got this backwards, but anyway, yeah, this should be on the other side. It doesn't matter. So you've got your X prime, Y prime, and Z prime here, and you've got your S, X, Y, Z, okay? And now you do all of this, and then you do all of this, right? And then you apply the result of this to the result of this, as opposed to, think of parallel as a zipper, right? So I'm zipping this with this, and this with that, and this with that, right? So I run S on X applied to X prime, Y applied to prime, Z applied to Z prime, right? So it's not parallel in the sense of, execution. It's parallel in the sense of wiring circuits.
Okay. So this doesn't tell us about something that is it our language sequential or right?
This part of it doesn't say the sequentiality versus parallel that you're talking about is all bound up in the operational semantics of the K. So if we go back up here.
Oh, yeah, I see.
Right? So we've got a K, it takes two terms, and then there's a rewrite. Right? So in the case of lambda, this is the rewrite. Application is the K. The abstraction is the first term, and the argument is the second term. Right? And then this rewrite is all you need to establish sequentiality. Right? Whereas here, right, par is the K. The first T is the for comprehension, and the second T is the output, and then the com rule is the rewrite. And this plus some other stuff is what gives you the interpretation of this as parallel composition.
I see. And this is why if we have only one identity, then this means that we are definitely sequential, right? We have only one direction.
There's a relationship there, but like notice that there's one identity, but for par, but because it's par is commutative, it's both a left and a right identity. So it's not just that. Yeah, it's the combination of having one identity and the operator not being commutative, and some other stuff.
Okay, thanks.
Sure. Someone else had a question?
Yeah. So my question is more basic, more higher level. So 2 weeks ago, Greg, you gave the example of a chemical reaction of, chemical reactions have certain behaviors. And if you want to find, you're looking for a particular type of behavior, you compare it to all these assortment of chemical reactions and their behavior to come up with the one that you want. So what you've gone over today, is this kind of, would one think of it as sort of the machinery of how these behavioral types work?
Yes, that's right. So what I've given is a generalized approach to behavioral types. So a little bit of history. So there are two camps or two branches of study of behavioral types, two major branches right now. So one is the Kairos behavioral types.
Mm-hmm.
And those are all model theory driven, in the sense that like spatial and behavioral observations and a logic for the pi calculus is all given in terms of a model, not in terms of proof rules. And they have a particular flavor in terms of what you can say with them. And then there are session types. And those are those work more in terms of a proof theory, and how the two fit together, in particular how the negation of the session types relates to Kairos's negation, is quite interesting. So what we've done is we've given a system that unifies those two branches. And allows us to talk about the relationship between the sessions and the negations and the models.
Oh, interesting. Okay.
Yeah. So all of it is unified. We got one system, and it automatically gives us sessions, and it automatically gives us. So remember when I said, hey, there are these multiple negations. So these negations are related. Sorry, these negations here. I'm not sorry. This one and this one are related to sessions, and these are related to the Chi-Ray style types.
Okay.
And there's other things as well, but basically what we've done, this is given a single algorithm which accounts for all of those different phenomena.
Mm-hmm. Yeah,
and it's expressed in terms of these, right? So
mm-hmm.
the input is a graph-enriched monad, and the output is a graph-enriched monad. Yeah, and the one thing I haven't talked about is how nominality works. So in other words, how variables and all of that stuff fits.
So my approach to trying to understand what it is you're explaining is I kind of run this simulation in my mind of this chemical process that's happening. You know, I'm looking for a particular behavior of a chemical process. And when you talk about, you know, supplying a resource or restricting a resource, you know, context and so forth, I'm kind of following along this process, chemical process in my mind as far as what's happening and how it interacts with all the various different behaviors. So is that in a sense, is that
that's right,
appropriate to do?
Yeah. So just to be clear, K is what is forming the left-hand side of your reaction rule, and rho is your reaction rule. And an S of rho says exactly what's on the left-hand side. And T, so source of the rule and target of the rule, left and right-hand side of the rule. So all of this data here is describing the reaction rule. And then the context is saying that we can suspend reaction rules by knocking a hole in. Notice that you know, like these give us generalized molecules, right? So in the sense that I could have K iterated, I could have a K of a K of a K of a K of a K, right? Whereas you can't replace a piece of a water molecule with another water molecule. So that's different in chemistry. This is like generalized chemistry.
Okay.
If chemistry were fractal, then you know this would account for all of the fractal behavior of chemistry.
Right, and that's